We are going to start functions. As we completed relations in the previous classes, here in this class we are going to start what functions. As I mentioned you, all these concepts, sets, relations, functions and further limits, limits, derivatives, integration, everything are different parts, different topics of calculus. Okay, so functions is a subtopic or sub-branch of calculus. So what is calculus and what are functions? That's what we are going to discuss first. Calculus. Calculus is a branch of mathematics which describes changes in different objects. Once again I am repeating, changes in different objects. If you observe everything in this universe, okay, the permanent thing is only the temporariness. Change is eternal. Okay, change only happens everywhere, and sometimes we are able to observe that change, and sometimes we are able to measure that change, and sometimes we can't identify it. Okay, for suppose if you observe a building, if you observe your school campus, if you are daily going to school and coming out, so you can't find any change in the shape of the building, in the structure of the building. The building shape and the building structure and the building stamina also gets changed by day, but usually we can't observe. But if you come after 10 years, if you come after 50 years, you will observe a calculated change, right? If you observe a good change in that building, not only in the building, the height of a person, okay, everywhere, in the height of the person, age of the person, stamina of the person, or you may say, everywhere, okay, or if you observe a plant also changes day by day. Everything in this universe usually changes from time to time, from day to day. Okay, see, for some changes we calculate the change easily, and sometimes we can't calculate the change easily, but the change happens. Sometimes we observe the change easily, and sometimes it is difficult even to observe the change, but there is change. Okay, see, calculus is capable of dealing with that change. Okay, calculus is the branch of mathematics which deals with changes, of objects, or changes of objects or things of the universe. Since it deals with the changes, and that change is an eternal thing in this universe, so calculus is much important in day-to-day life and in regular applications. Okay, so and that's why usually you use calculus repeatedly in your physics and then engineering related topics. Okay, right. And in that calculus, the first step we need to learn is functions. So every part of the calculus usually works on observing the change, works on measuring the change, works on estimating the change, works on expecting the change, and everything, right? There are different branches, different subtopics of the calculus. Each topic just analyze the change of certain object, analyze the change, calculate the change, estimate the change, expect the change. Okay, see, it completely deals with changes of object, anything if you take. Okay, right. See, function is also one such a topic, one such an item, and if you observe anything, the change happens with respect to the change of the other. Okay, for suppose height of the person changes with respect to time, with respect to days, with respect to months. Is it right? Or for suppose if you take any other thing, for suppose I am giving you one example here, shadow of a tree. Shadow of a tree, how it changes? See, if you observe, shadow of a tree usually changes depending upon sunlight. Okay, position of the sun, actually we say specifically here as sunlight, as well as height of the tree, length of the tree. You say, see, for suppose if I am going to observe the shadow of a tree, that shadow of a tree changes for different, for suppose I have different trees with different lengths, their shadows are different, and the shadow of tree also changes, the length of the shadow is different at different position of the sun. So shadow of a tree usually depends on the sunlight as well as the length of the tree. and here you can express the shadow of the tree is depending on sunlight as well as length of the tree. What I have to say, sunlight as well as length of the tree. So shadow of a tree or length of the shadow is dependent on sunlight as well as the height of the tree. And in this case we say that shadow of the tree is a function of light of sunlight as well as the height of the tree. That means the shadow of the tree changes with respect to change in the position of the sun as well as with respect to change in the height of the tree. Is it right? And so shadow of the tree also changes. Here if you observe this L, H are LH and S. L is the position of sunlight, I just keep it as L. H is the height of the tree. This L and H are usually mentioned as what? They are mentioned as independent variables. They are mentioned as independent variables. Whereas this S, if you think, this length of the shadow is depending on the sunlight position as well as the height of the tree. That means this length of the shadow is depending on those two objects. That's why we call it as dependent variable. See, as a first point of the function, I am discussing everything in a general way first of all. Okay, this is a general way of discussion. And in the second point, I will mention mathematical way of introducing, mathematical way of defining a function. Okay, you will get some more clarity in that second point itself. The first thing is generally what is a calculus, generally what is a function. That's what I am discussing. I will give you one more example. For example, if you say area of the square, I have a square and its area. What is the area of the square? We know it as S square. That means area of the square is depending on the side length of the square. If you change the length of the side of the square, area also changes. And here in this case we say that area of the square is a function of S and we represent it like f of S. See, why we are calling that area as a function of S? Because if S functions, if S works for different values, if S changes for different values, area also changes. Okay, so here in this case, if you observe, this S is mentioned as independent variable. You need to change S. If side length is 2, area is 4. If side length is 5, area is 25. Like that. Okay, if S you have to change, and depending on that S, area will change. And since this area is depending on that S, we call it as dependent variable. At the end, what I am going to tell you is simply calculus deals with the change of the objects, so that function as well as the limits and every concept deals with the changes, and in particularly functions is a backbone for all those things. And in these functions usually we will observe a relation between the variables. Why? Because change in one variable is dependent on the change in other variable. Okay, change happens with respect to change in the other thing. Okay, just like height of the person changes with respect to time. See, time is always changing in this universe. So usually we will express change in every object with respect to time. Okay, and some special problems will usually happen, like area of the square is depending on the side of the square. Shadow length of the tree is depending on sunlight as well as the height of the tree. That means length of the shadow will change with respect to change in the sunlight position, with respect to change in the height of the tree. Area of the square will change with respect to change in the S. So in the chapter functions, we usually identify such relations. Okay, we usually identify such relations, okay, such connections between the variables. And in further chapters, we are going to identify, we are going to observe the change in the dependent variable with respect to change in the independent variable. All those things will happen in the further chapters. But in particular here in functions, what we are going to do? We are going to establish the connection. We are going to establish the relation between the variables first. And after establishing the relations between the dependent variables and the independent variables, we are going to measure the change in dependent variable with respect to change in independent variable. Okay, right. So these are two simple examples related to the function. This is the general way of discussion. And now in the second point, I will give you the mathematical way of definition. Okay, just have a look till now. Now, mathematical way of describing a function, mathematical way of defining a function. So already we discussed about the sets, relations and everything, right? For suppose if we have two sets A and B, based on those two sets A and B, we will usually write its Cartesian product A cross B. And after writing Cartesian product, we will find out some relations which are subsets of A cross B. How many relations are there? There are many relations, as many subsets of A cross B. Those many relations are there from A to B, right? And in these relations, okay, what I am telling you, right? Relations, okay? You just pay your attention now on relations. In these relations, some special relations are known as functions, okay? In these relations, some are functions. See, what is that speciality? Okay, what speciality will make a relation as a function? That's what we need to describe. Coming to the definition of a function, okay, a relation in which every element of the first set has unique correspondence with the elements of second set is mentioned as a function. Once again I am repeating you, when coming for the definition, function is a relation. Function is a relation in which every element of first set, in which every element of first set has unique correspondence or unique relation, you may say anything, no problem. Unique correspondence with the elements of second set. Right. This is basically the definition of a function. So mathematically a function is a relation. You need to identify it. Functions are nothing but relations itself. There are many relations from A to B. Among those many relations, we are going to identify some special relations which are satisfying this particular property, and we call those relations as functions. And the property is that every element of the first set has unique, I am underlining again, has unique correspondence with the elements of second set. Okay, here in particular, if you have two sets A and B, Cartesian product A cross B, relation R is a subset of A cross B, we usually say that the relation R is from A to B as the notation. Here, this A and B, if you observe, this A is the first set, whereas that B is the second set. Is it right? This A is set 1, this B is set 2. And as per the definition, every element of first set, every element of the first set has a unique correspondence with the elements of second set. That's the basic definition of a function. Okay, right. When you wish to give a set builder notation for the function, it's actually a relation, right? And when you try to give a set builder notation for a function, I will give you in such a manner. Okay, just have a look. Yeah, a function f, right, contains the ordered pairs x comma y. Because every relation contains the ordered pair x comma y, function is also a relation, so it also contains ordered pairs x comma y. A function contains ordered pairs x comma y such that for every x belongs to A, such that for every x belongs to A, there is unique y in B. That's the basic definition of the function, and this function is a subset of A cross B. Okay, see, f contains the ordered pairs x comma y such that for every x belongs to A, there is unique y in B. Okay, that's the definition in terms of words. This is the definition in terms of what? Set builder form. For every x belongs to A, there is unique y in B. Okay, this is the basic definition. I will give you some examples. Those examples will clear your confusions. Okay, I will erase this definition. You just have a screenshot and then I will give you few examples. Right? You just take some elements in set A and some elements in set B, and there you just try to define some relations from their functions, and among those you just identify which are functions and which are just relations and everything. Okay. You just memorize it once again. Every element of first set has unique correspondence with the elements of second set. Okay, I am erasing this, so you have to memorize it. Every element of the first set has unique correspondence with the elements of second set. Every and unique. These two words you need to pay attention on these two words. Every of the first set, unique of the second set. Okay, you just take some examples. Take set A having the elements, say some 1, 2, 3, and take some B having the elements A, B, C, D. Right. If you have like this A containing the numbers 1, 2, 3, B with A, B, C, D, then it is very clear that n of A cross B is equals to 3 into 4, which is 12. Since n of A cross B is equals to 12, then number of relations. That implies number of relations from A to B is equals to 2 power 12. So what's the value of 2 power 12? The value of 2 power 12 is 4096. So we have nearly 4096 relations from A to B. And among those 4000 relations, few relations are functions. Okay, and we are going to identify those, and I am going to give you examples like this. Just have a look. Okay, I will take the first set A with the elements 1, 2, 3, and the second set B with the elements A, B, C, D. Okay, right. So I will just give you one relation. Okay, yeah, you just look there here. 1 to A, 2 to B, and 2 to C. So this is relation 1. Right. Is it a function or not? That's what we need to check. Is it a function or not? See, for sure this is not a function. Why it is not a function? Because as per the definition, every element of the first set has a unique correspondence with the elements of second set. See, for every element of the first set we need to have a map, we need to have an arrow, but here for 3 there is no such arrow, so it is not a function. Okay, this is one relation just I mentioned you, that is not a function, right? Likewise, we need to check, we have to check, we are able to check those 4000 relations whether they are functions or not. Okay, I will give you another example. In the first set you just take the elements 1, 2, 3, and in the second set you just take the elements A, B, C, D. And now I will give you some arrows. Okay, yeah, 1 to A, 2 to B, 2 to C, 3 to D. You may say it as a relation 2, right? What you say about it? It's purely a relation from A to B. Whether it is a function or not, that's what you need to check. And if you check, every element has a correspondence. Okay, no element is empty in this first set, so first property is clear. And whereas coming to the second property, every element must have unique correspondence. I am repeating, unique correspondence. One has unique correspondence A, 2 has not unique correspondence. 2 is just going to B as well as going to C. Okay, 3 has unique correspondence. 3 has unique correspondence. 1 has unique correspondence, but 2 has 2 correspondence here, not unique. Okay, and that's why this is again not a function. Okay, so now I will give you one other example. Just look there. The first set contains 1, 2, 3, and the second set contains A, B, C, D. Now I am giving you another relation, you may say R3. Okay, right. 1A, 2B, and then 3B. What you say about it? Okay, this is relation R3. What you say about it? Whether it is a function or not. To check, you need to follow the rules. The first thing is every element has a correspondence. So 1 has a correspondence, 2 has a correspondence, 3 has a correspondence. No element is empty here. Okay, first thing is okay. Second thing, we need to check for the unique correspondence. 1 has unique correspondence A, okay. 2 has unique correspondence B, okay. 3 also has unique correspondence to B, okay. So every element has correspondence and that correspondence is unique, and for sure this is a function. Okay, see, as per the definition, every element of the first set has unique correspondence with the elements of second set. That's the definition. Okay, that's why you need to check the elements of the first set, see, so that each one should have a correspondence. Okay, don't bother about the elements of second set. Okay, if they are empty, nothing will happen. The definition is acceptable. Okay, the definition is satisfying by this relation. Okay, no need to bother about these elements. Okay, and one more thing, every element has unique correspondence. You just look here. Here 2 is corresponding to B only. 3 is corresponding to B only. So 2 has one correspondence only. 3 has one correspondence only. So the definition is satisfied. But whereas coming to the second relation, 2 has two correspondence. 2 is corresponding to B. 2 is corresponding to C also. Here this 2 has two correspondences. But as per the definition, we need to have unique correspondence. So 2 fails that unique correspondence property, and that's why it is not a function, but it is a function. In general, if you see, there are 4000 relations, right? So you just take 4000 relations, check everything whether it is a function or not. In that way, if you check in any relation, if you find these type of arrows, okay, which type of arrows? If you find, I am giving you here, if you find these type of arrows starting from one element to many elements, these type of arrows are not generates a function. Whereas if you face these type of arrows, and they are just corresponding to function. Okay, right, just to avoid your confusion, I am giving you this mark. Okay, just have a look, and this is something basically related to the functions from relations. Okay, so in third point, we are going to identify number of functions. Okay, for suppose if you take the number of elements in set A as m and the number of elements in set B as n, A contains m elements, say them as a1, a2, a3 and so on am, and B contains n elements, say them as 1, 2, 3 and so on n. And now we are going to count the number of functions. Okay, right. See, as per the definition of the function, every element must have a correspondence with the elements of second set, and that correspondence must be unique. Is it right? Okay. For suppose if I start an arrow from A, I am starting an arrow from A. See, I am starting an arrow at A, and to which point of B, to which element of B I need to reach. See, there are no restrictions in reaching B. Okay, start at A, you just reach to B1, B2, B3 to any element of B, no problem. It won't disturb the definition of the function. Okay, but you need to start only once at A1. Okay, you need to start only once at every point of the first set, and you must draw an arrow. Okay, for every element of the first set, you need to draw an arrow, and you need to start only once, but you have no restrictions in reaching elements of B. Okay, so you just start with A1 and reach any element of B. That in the sense, this element A1 has n chances. Okay, A1 has n chances to correspond or to relate. Okay, and similarly, when you start from A2, again A2 has n chances. Here there are no restrictions with us. Okay, for suppose if A1 reaches to B2, then you just start with A2. A2 may reach to B1, A2 may reach to B2, A2 may reach B3, no problem. Again if A2 reach B2, no problem, still it is a function, right? That in the sense, A2 again has n chances, and A3 again has n chances. And likewise, if you continue, every element of the first set has n chances. So since every element has n chances, while calculating the total number of chances, n into and so on into n for m times, because there are m elements in the first set, every element has n chances, so you need to multiply n for m times, and that is equals to n power m, and which is nothing but n of b to the power n of a, and this n of b to the power n of a, n power m represents number of functions from set A to set B. Okay, just have a look. So now in B, just go with an example. A is equals to 1, 2, 3, B is equals to A, B, C, D. From there it is very clear that n of A is equals to 3, n of B is equals to 4, and as we discussed, n of A cross B, number of elements in the Cartesian product is equals to 12. Okay. And now number of relations from A to B. Okay. Number of relations from A to B. Number of relations from A to B is equals to number of subsets of A cross B, which are nothing but 2 power n of A cross B, and that is equals to 2 power 12, and you may say 2 power 10 is 1024, 2048, and then 4096. These are the number of relations. And now if you count number of functions from A to B, number of functions from A to B, okay, as per the derived formula, number of functions are simply nothing but n of B to the power n of A, number of elements in the second set to the power number of elements of the first set. Here number of elements in the second set is what? 4, and the number of elements in the first set is 3, and 4 cube is how much? And 4 cube is equals to 64. Just think about it. From set A to set B, how many relations are there? 4096 relations are there. Among those 4096, there are just 64 functions, and all the remaining are not functions. Is it clear? So functions are that much special. Okay, among 4000 relations, there are just 64 functions. And see, if to analyze the relation between the first set and second set, these functions are much comfortable actually. Okay, so number of functions are 64, and sometimes the questions may ask you to find number of relations which are not functions. Number of relations which are not functions. Okay, just observe the sentence of the question, the format of the question. Number of relations which are not functions. Number of relations are totally 4096. Among those 4096, number of functions are 64. See, in 4096, only 64 are functions and the remaining are not functions. Okay, so 4096 minus 64 is your answer, and which is simply 4032. So from set A to set B, there are 4032 relations which are not functions. You need to memorize these formulas also. After having n of A and n of B, what is n of A cross B? What are the number of relations and number of functions, number of relations which are not functions. Okay, have a look. Go for a screenshot.